Let's look at this interesting problem from Putnam, which is arguably one of the most difficult math competition in the whole world. The median score is often 0 or 1 out of 120. This is question A6 from the 2023 Putnam Math Competition. Alice and Bob alternately pick integers from 1 to n. Before the game starts, Bob selects a goal, either odd or even fixed points. A fixed point is defined as follows. The number k is a fixed point if it is chosen on the kth turn. Bob wins if the parity of fixed points matches his goal at the end. So the question is, for which values of n does Bob have a winning strategy? Let's look at the case where n is even. Let's start with the simplest case, n equals to 2. If Alice picks 1 and Bob picks 2, there are 2 fixed points. If Alice picks 2 and Bob picks 1, there are 0 fixed points. In both cases, there are even numbers of fixed points. We can generalize this and show that Bob has a winning strategy when n is even. He ensures that the number of fixed points remains even. Consider a pair of numbers 2k-1 and 2k, where k is a positive integer. Note that Alice always acts on an odd turn. Therefore, if Alice chooses 2k, the number 2k must not be a fixed point because it is even. Similarly, Bob always acts on an even turn. So reacting to Alice's choice, Bob can choose the number 2k-1 to keep the number of fixed points unchanged, as the number 2k-1 also cannot be a fixed point. On the flip side, if Alice chooses 2k-1 on the 2k-1 turn, Bob can choose 2k on the 2k turn. This adds 2 fixed points. If Alice chooses 2k-1 on any other turns, Bob can choose 2k on the subsequent turn so that both numbers are not fixed points. Therefore, Bob has a winning strategy when n is even. First, select a goal of even. Then, divide the numbers into pairs 1 and 2, 3 and 4, and so on. When Alice picks a number, Bob picks the other in the pair. In every 2 turns, fixed points either increase by exactly 2 or remains unchanged. Then, we move on to the case where n is odd. Let's start with n equals to 1. Alice picks 1 and then creates 1 fixed point, so there is an odd parity. For n equals to 3, if Alice picks 1 and Bob picks 2, there are 2 fixed points. If Alice picks 2 and Bob picks 1, there are 0 fixed points. Lastly, Alice is forced to pick 3, which creates 1 more fixed point, so there are an odd number of fixed points. Finally, if Alice picks 3, Bob can pick 2, and then Alice picks 1. This creates 1 fixed point, and the number of fixed points is also odd. We can generalize to show that Bob has a winning strategy when n is odd. If Alice picks 1 and Bob picks 2 or vice versa, this keeps the number of fixed points even. Now only the numbers 3 up to n remains, and we start from the 3rd turn. So, Bob effectively reduces the game to the case of n minus 2, which is just a smaller case of odd n. If Alice chooses a number y greater than 2, Bob can choose 2, so there is 1 fixed point. Then, Bob can implement the following rules. Rule 1. When Alice picks a on the 8th turn, Bob can pick a plus 1 on the a plus 1th turn. This is pretty straightforward because when Alice creates a fixed point, Bob also wants to create a fixed point, so that the parity remains odd. It is crucial to assume that a is not equal to y minus 1 because Alice already picked y on her first turn, so Bob is unable to pick y on the a plus 1th turn. Let's say if Alice picks a number not equal to A on the 8th turn. Then, Bob can pick A plus 2 on the A plus 1 turn if available. This can prevent Alice from creating a fixed point on the next turn, because she would be unable to pick A plus 2 on the A plus 2th turn. Otherwise, Bob has at least 2 choices remaining, because n is odd, so Alice must be the last player to pick a number. Bob can then choose whichever number that does not create a fixed point. Lastly, if Alice picks y-1 on the y-1th turn, and the number y is not available because Alice has already picked it on the first turn, then Bob can pick the number 1. This changes the parity from odd to even. Note that after Bob's turn, all the numbers from 1 to y are picked away. This statement is proved later. And then, there are only n minus y numbers remaining. Therefore, this transforms the game into the case of n minus y. Because Alice plays on odd turns, y-1 must be odd, and hence y is even. This makes n minus y odd, and the game is effectively reduced to another case of odd n. Finally, Bob wins by selecting a goal of odd and implementing the strategy above. To prove that all the numbers from 1 to y are picked away after the scenario in Rule 3, we should consider the following lemma. The converse of Rule 2 states that if Bob picks A plus 2 on the A plus 1th turn, then Alice must have picked a number not equal to A on the 8th turn. Otherwise, if Bob did not pick A plus 2 on the A plus 1th turn, then Rule 1 must have occurred. That is, Alice picked A on the 8th turn. The conclusion is that if Bob did not pick A plus 2 on the A plus 1th turn, this implies that Alice picked A on the 8th turn. The scenario in Rule 3 only happens if Bob did not pick y-1 on the y-2th turn. So by lemma 1, Alice picked y-3 on the y-3 turn, and Bob reacted by picking y-2 on the y-2th turn. In this case, both the numbers y-2 and y-3 are gone in the previous turns. Using the same argument, the scenario where Alice picks y-3 on the y-3 turn can only happen if Bob did not pick y-3 on the y-4th turn. Therefore, this implies that Alice picked y-5 on the y-5th turn, and Bob reacted by picking y-4 on the y-4th turn. By induction, all the numbers from y-2 down to 3, as well as y and 2 from the first 2 rounds, are already picked before Rule 3 occurs. When Rule 3 occurs, y-1 and 1 are also picked. Therefore, all the numbers from 1 to y are picked, and the game reduces to the case of n minus y. To conclude, Bob can always win by selecting the goal even when n is even and odd when n is odd. If you enjoyed this video, please give it a like and subscribe to my channel. You can also view the full written solution at the link in the description.